All right. Sorry, I'm a bit late today. I have had discussions now with my PhD student. So just finished. So let's continue with the implantation process, the final parts. Let me share the screen. Okay, can you see the slides? All right. Before this, we have stopped here. So we have discussed until shadowing effect during ion implantation. So due to presence of features on the surface of the wafers, for example, if you have polysilicon on your silicon wafer. The polysilicon here is usually thin film. We're going to learn later on today in a topic we call it thin film deposition, TFD. So you can deposit polysilicon layer on your silicon wafers. So due to the presence of structures such as polysilicon or other structures, other materials, uh, we will end up having some areas being shaded during ion implantation process. So that can be compensated by having a post-diffusion process after the implantation, because we know that the nature of the diffusion involve a vertical, diagonal, and lateral diffusion of the impurities of the dope region, so that you can compensate the areas being shaded during ion implantation, so that you can cover the whole areas that you want to dope. So we've also learned that ion implantation is a high energy process, even though we have low energy, middle energy, and high energy. But essentially, the nature of the implantation is of high energy, bombarding the ions into the silicon to form the junction, form the depth into the silicon wafers. So when you say that it's a high energy process, then it's going to involve some damage to the silicon lattice after the process. So that's what we're going to look at today, and how do we repair the damage after the implantation process. So implanted ions transfer energy to lattice atoms upon impinging to the lattice, upon impinging to the surface of silicon. So it carries together, the ions carry together some levels of energy to be implanted, to enable implantation. So results in atoms from the lattice break free. So the free atoms collide with other lattice atoms, and more lattice atoms, and more lattice atoms. So the damage continues until all the free atoms stop from the movement, or from triggering another collision with another lattice atoms. So one energetic ion from the implantation process can cause thousands of displacements of the lattice atoms. So this is the damage that we are talking about. So depending on the energy level that you have during the implantation process, either it's low energy or middle energy, or a high energy process. So the higher the energy it carries, the more damage it causes to the silicon lattice. So as an illustration, if you're talking about ion or heavy ion with different energy level, for example, it's going to cause different levels of damage, different kinds of damage to the lattice, right? Some can cause a thin but long one, but heavy can cause a wider area in a more localized region, for example. but it still depends on the energy that we use during ion implantation process. So the gray area here is your silicon lattice or the silicon wafer. So that's the amount of damage it causes during the process. So this process, it carries a higher level of accuracy when we talk about the doping, but then it also leads to some damage problem after the process. So in comparison to the diffusion method that we discussed before, it's more seamless in its nature, but then it causes less damage, but then the accuracy is not as good as implantation process. So ion collides with lattice atoms and knock them out of lattice. So this is what essentially happens. So you're going to have distorted lattice during the process and after the process. So implant area on substrate becomes amorphous in structure. So bear in mind that we use monocrystalline silicon for the IC fabrication. So they are monocrystal. So it's infinite range of periodic arrays of atomic arrangement. So, but after the implantation process, the affected region becomes more amorphous due to the distortion to the lattice, right? So this before the process is mono as the original material. So after the process is amorphous due to the distortion of the lattice. Right, a dope must in single crystal structure and bond with 4 silicon. We discussed this one last time, that silicon has 4 neighboring atoms, so they're covalently bonded to 4 neighboring atoms. So in order to incorporate either p-type or n-type, they have to be substituted, and we've discussed that typical dopants such as boron and phosphorus are usually substitutional in nature instead of interstitial. So they have to be present and have to be substituted in the lattice position. Thermal energy from high temperature helps silicon to recover to single crystal structure. So after the process, knowing that your monocrystalline is now turned into amorphous lattice, amorphous structure, so we can actually recover the amorphous structure back into monocrystalline by supplying high temperature or high thermal energy. So it can be done in order to repair the defective structure, right? For example, so this if you look at the gray atoms, so it's down here, so imagine that they are monocrystalline silicon, right? Infinite periodic arrangement of the silicon atoms. So the moment you incorporate dopant, for example, if you say this one is phosphorus, then this one is also phosphorus, right? So you can see that the lattice is now being distorted. So by applying high thermal energy, so for example, to repair the defects, and this can be done by a process that we call annealing. Annealing process. Annealing is usually done for many purposes. So one of the purposes is called defect repair, right? We can also do annealing for some other purposes. For example, if you want to turn your Schottky contact into ohmic contact for your metallization, then you can also do annealing. You can also anneal defects. You can also anneal to improve addition, for example. So it can be for many different purposes. But for this particular case, we're going to use annealing process to repair defects caused by ion implantation. So let's look at the evolution of the lattice. The moment you supply high temperature process by annealing. So say if you run this process at 900, 1000, for example, for some time. So assuming it's 1000 degrees C process, so you can see how the the lattice defects are being being perfected over time. Right, so it improved a little bit in terms of the crystalline arrangement. So if you look at your lattice atoms of your single of your monocrystalline, so instead of being only single row, so you can see the next row coming in, which shows that the defect being perfected. So lattice defects are being perfected. So now you have your second row coming as your monocrystalline lattice again. So now you have your third row coming, right? You have your third row coming in. So that means your lattice is restored from amorphous to monocrystalline again. And the dopants are still there, already incorporated into the lattice to do the doping, right? So more coming, more arrays are coming in, more arrays are coming in, right? So that's the evolution. So basically what you see here is before annealing, after implantation, before annealing, so it's amorphous in nature, amorphous silicon, but after you finish the annealing process, it's going to be completely monocrystalline silicon as the original version of the silicon wafer that we use for the IC fabrication, right? So all defect repair or defects annealing can be called defects annealing. So the process is called annealing, right? Finish. Okay, any questions on implantation? I'm going to move to the next one. Do you have any questions on implantation in particular? I'm going to move to thin film deposition today. Ada soalan? Everything okay with implantation? All right, all good. So let me share our next slide. Film deposition. Okay. Right, you can see the slides. All right, good. So we're moving to film deposition. We're going to talk about how do we deposit a very thin layer of something. So it can be many different materials. So you can deposit silicon dioxide. You can, in fact, deposit silicon as well. You can deposit silicon nitride, silicon carbide. You can deposit metal contacts such as silver, aluminium, titanium, palladium. So it can be done by various processes. So they are together, they are called film deposition. In fact, you can also do wet processing to deposit your film. For example, if you want to deposit your zinc oxide by spin coating process, or a chemical bath deposition, or well, some other electrochemical perhaps. So it can be considered a film deposition as well. Right, so let's recap a few things before we move on to film deposition. So what are the major differences of ion implantation and diffusion process? What are the major differences? Anyone would like to answer this? And write down, or you can talk. Ain, what are the major differences? Ain, Natasha. Fatimah Zahra. Apa beza ion implantation dengan diffusion? Can write down. Right? Ion implantation is more expensive. Okay, what else? Ilham, apa lagi, Beza? Ion implantation and diffusion process. Fazira, okay, Amira, diffusion, high temperature. Ion implantation, yes, doesn't need high temperature. Right, Fazira, diffusion, isotropic. Yep, good. Ion implantation, anisotropic. Lagi? Apa lagi? Maybe another one or two. Apa lagi yang kita baru belajar tadi? How about the damage? Right, you can also mention in terms of damage, yeah. So least disadvantages of ion implantation, some have been listed already, right? So how to eliminate defective regions, clear. So we've done annealing processes now, and we've seen how the lattice is restored from amorphous silicon due to the high energy implantation back to monocrystalline silicon as the original condition. All right, so let's move on to thin film deposition. So it's quite a wide area to cover. So, however, I'm going to look into the most important ones. We can divide film deposition into multiple areas, and each of these areas is quite big already in its own. So, for example, we have a PVD technique or PVD methods. We call it physical vapor deposition, or we call it PVD. And this involves evaporation and sputtering process. So some of you might have done some of these processes before during your FYP. So we have evaporation, which can be further divided into thermal evaporation and electron beam evaporation. So these are the common ones. So the next one is called sputtering. So we have sputtering in our lab. So the same like evaporation, we also have e-beam and thermal evaporation in our lab. So as for sputtering, we can do it by either DC or RF process. So DC is direct current and RF is radio frequency. Okay, DC is direct current and RF is radio frequency. So we need to use different mode, either DC or RF, in order to deposit different materials. So depending on the type of materials they want to deposit. On the other hand, instead of PVD, we also have another big method that we call CVD, or chemical vapor deposition. And in CVD, we have a range of different deposition techniques. So yang saya letak kat sini tak semua, saya letak ni kat sini just a couple of the CVD methods only. So we have PECVD, plasma enhanced CVD, plasma enhanced chemical vapor deposition. We have LPCVD, low pressure CVD. We have APCVD, atmospheric pressure CVD. We have HWCVD, hot wire CVD. Right. Now, first one, plasma enhanced. Second one's low pressure. Third one, atmospheric pressure. Fourth one, hot wire. Hot wire. Wire panas. Hot wire CVD. We also have AACVD. Saya tak letak semua, saya cuma tambah apa yang saya ingat lah, because there's a range of CVD materials. Because the moment scientists found a new CVD approach, then they will name the new approach as a new name, and then they publish, and then the next scientist coming in and cite the name, and it becomes a new method. AACVD is atmospheric assisted CVD. Atmospheric assisted. Atmospheric assisted CVD. Can dia ada dash line between atmospheric assisted CVD. So you may have read some other CVD techniques. Ataupun kalau you Google CVD, then you'll probably see some other new names as well. And the third one is called epitaxial technique, where you do a very accurate atom by atom deposition by this technique. So, sorry, sebelum lupa, we also have for CVD you also have MOCVD, metal organic CVD. Yang ni yang ada kat Aino for blue LED punya preparation. It's called metal organic. Metal organic. So we have this in Aino US CVD, right? MOCVD untuk apa? Blue LED deposition, nitride based deposition. In fact, OSRAM pun pakai MOCVD untuk prepare dia punya LED, front end fabrication. Right, epitaxial techniques, we have MBE, molecular beam epitaxy. Kita ada dalam NOLAB, but then kita dah tak pakai. But it's too expensive to maintain and too expensive to run. We used to run nitride deposition on this MBE, but now no more. Tapi equipment tu masih ada. We're gonna dispose of the equipment. Lupuskan dia. MOVPE, metal organic vapor phase epitaxy. Metal organic tu sama, metal organic vapor phase epi epitaxy. LPE is liquid phase epitaxy. So we have range of different deposition techniques in order to deposit a range of different materials. You can deposit elementary material, binary, yang lagi complicated lah, quaternary and so on and so forth. Ternary, quaternary, so on and so forth. Right, so before we start, vacuum. So let's learn a little bit about vacuum. So what is vacuum? What is vacuum? What do you understand by vacuum? Boleh tulis kat sini ataupun you can unmute yourself. What do you understand by vacuum? Anyone? Kita buat eksperimen kan, second year lab, vacuum technique. What is vacuum? Zero pressure, okay. Well, zero pressure is one example, one possibility. What else? What do you understand by vacuum? No air, okay, no air, all right, lagi? When we say vacuum, what crosses your mind? What is vacuum? Free space, okay, lagi? Liana, anything? What is vacuum? Can write down there. So kenapa page ni empty ni? Kenapa page sekarang empty? Sebab vacuum tak ada apa-apa. No matter, right? No matter. So when you extract your particles or your air content, moisture content, or whatever you have from a space, then the space can be turned into a vacuum. Right? How about the pressure of a vacuum? How about the pressure of a vacuum in comparison to atmospheric pressure? How do you compare the pressure levels? Kita punya atmospheric pressure sekarang berapa? 1 atm. 1 atm kan? So if you convert that into torr, for example, how big is the pressure? Can you try to search now? Cuba search. 1 atm, if you convert into torr, berapa torr? We have many units that we can use to show pressure levels, atm or torr or millibar or psi. Cuba check, 1 atm berapa torr? Yeah, 760, right? So 760. Cuba check, 1 atm is equals to berapa millibar? Millibar, m bar. Coba cek, coba Google. Yeah, that's about 1,000, right? So 1 ATM equals to 7. Saya recap di sini ya. 1 ATM equals to 760. Alamak, silap. Okay, so 1 ATM is equals to 760 torr and equals to 1,000 millibar, right? So when you talk about vacuum, then you're talking about a very low pressure. Typically, if you talk about IC fabrication or some other semiconductor device fabrication, then we're talking about 10 to the 3, 10 to the 4, 10 to the 5 torr, for example. 10 to the, mungkin ada yang dah buat apa ni? What do you call? FYPTCs on this, huh? Yeah, for example, 10 to the minus 5 torr. So in comparison to 7.6 times 10 to the 2 torr, which is atmospheric pressure, so it's like 6-7 orders of magnitude lower as far as a deposition process is concerned, right? So we're going to talk about how do we bring the chamber, the pressure in the chamber from atmospheric pressure typically down to that level, -5, -6. Some process even requires us to go down to -8, -9, right? Depending on the sensitivity of the device. So if you talk about cell, typically it needs down to -5, -6. If you're talking about more sensitive devices, then maybe you need to go down to -7, -8. Okay. Masih ingat lagi ke eksperimen yang dalam lab 200, vacuum technique? The simple experiment that you ran in lab 200. Ada vacuum technique ya? Right. To be able to do this, to introduce a vacuum in a space, you need to use vacuum technology. You need to use vacuum technology. You have to evacuate the space by using, range of vacuum technologies, mainly the pump that you need to evacuate the chamber. So talking about vacuum, so the vacuum can be in a rough vacuum level. So we're talking about, if you're talking about millibar here, millibar kat jadual ni. So that's about 1,000, more or less, 1,000 millibar in rough vacuum. Then you can bring it down to medium vacuum level, down to -3, right? You can bring it further down to high vacuum level, which ranges from -3 to -7. You can even bring it further down to less than 10-7, means 10-8, -9. That's called UHV, ultra high vacuum. Okay, so each vacuum region that we're talking about here, medium, high, ultra high, requires different pump to do the job. Okay, so you can see some of the information in the table here. So if you're talking about particle number per unit cube, so you can see a significant reduction from going from the left to the right, so less and less particles. So 1 ATM is equal to 760 torr, right? This is another unit to put it. So you can also see the illustration down here, how the high vacuum, rough vacuum, high vacuum, and the UHV looks like. So if talking, for example, 10 -3, right, then you have pressure of this much and number of particles per unit centimeter cube, right? If you go to a high vacuum, then for example, you may be operating at -6, so that's the amount of particle that you have. And if you go to UHV region, then you're operating somewhere -8 to -12. Then you're going to evacuate more and more particles with more advanced vacuum technology. So for example, to do the job, you can use rotary pump. So we have this pump in that. So rotary pump is going to take the pressure in the chamber from 1 atmosphere down to about -3. So if I can convert this to torr, and you're talking about 1 atmosphere or 760 down to 10-3, right? Torr. So that can be done by rotary pump. So for your information, each pump or each type of pump, it has its own operating region. Maksudnya rotary pump kat sini dia hanya boleh operate within this region from atmospheric pressure down to -3. So if you want to achieve a vacuum level beyond -3, so that means -4, -5, or even lower than that, you need to move to another pump. Okay. So for example, if you want to go for lower than -3, we can also use a diffusion pump. Diffusion pump. So this is another pump you have in your lab 200. You have a combination of 3 and diffusion. So diffusion can take it down from -3 or -4 down to around -6. Right? So this is the operating region of diffusion pump. So you can use, if you want to go for below that, you can move to turbo molecular pump. Right? So, lagi rendah dia punya vacuum level, so the more expensive the pump gets, because it needs to evacuate more. It has to have a better capability, faster speed, and stuff like that in order to evacuate the chamber to get to the vacuum level that you need. Right. So now let's look at PVD. PVD is physical vapor deposition. So any one of you have tried any evaporation technique before? Ada yang pernah buat evaporation waktu FYP? Evaporate metal contact ke, evaporate apa-apa ke? Has anyone tried before? You can evaporate many things, particularly silver. Oh, bukan silver, particularly metal. Aluminium ke, silver ke, whatever that is of low melting point. Right, so we're going to see later on, but this is more or less what happens. The evaporation that we have in our lab is located in the sputtering room. Kalau biasa buat sputtering, next to the control room, we have evaporation at the far end near the window facing TI, Technology Industry School. Right, so what's actually happening during the process is you're going to melt the material that you want to deposit. For example, if you want to deposit aluminium, contohnya, evaporate aluminium contact, so you need to use aluminium wire. You have to cut the aluminium wire, the long one, into small chunks, right? The smaller the better, because the smaller the chunk you have, the surface area is higher, so it's a lot easier to be melted and to be evaporated to your sample. So the sample is going to be melted, right? So you're going to form a liquid there, and then the liquid is going to be evaporated. So, but beforehand, you need to have your chamber to be evacuated down to maybe around -4 or -5, maybe. Usually, kalau metal, we can do that at -4. -5 is a safer pressure level. So we call this as base pressure. Base pressure. Right? So then the material is going to be evaporated, then it's going to turn into gas phase. So it's going to go up to your sample. And I'm going to explain how does it work. It's going to go up to your sample. For example, if you have silicon or glass or whatever, ataupun dah ada layer ataupun sample on the sample, so it's going to be evaporated on your sample, so in transport phase, and then it's going to condense. It's going to be condensed into solid phase, and then they can end up on your sample ataupun on your bare glass ke, bare silicon ke. So this is more or less what's happening to the material in PVD process. Nanti if you look into any specific process, then it's going to be slightly different. But generally, this is what it experiences: evaporation, transport, condensation. Then you get your material on the substrate. Right. So now let's look at evaporation. Tak ada orang yang pernah handle evaporation system ke? Tak ada anyone of you yang buat evaporation ke? Aluminium ke, silver ke, tak ada? No one? Right, so this is how it looks more or less, a simple representation of an evaporation chamber. So this square box is actually a chamber. Process chamber lah, process chamber. You have your source. For example, if you want to evaporate aluminium as your contact, then you need to cut your aluminium, put in the tungsten boat. I'll show you how later on. Then you're gonna pass some current through. It's called resistive heating. Resistive heating. Resistive heating because we supply some current through the tungsten boat, or we call it tungsten wire lah, tungsten wire, and then it's gonna turn hot. Then it's gonna melt your aluminium into the liquid form, and then it's gonna be evaporated, changing into gas phase, evaporated, transport, and landed on your sample. So your sample is here. Substrate is your sample. So it's gonna be a distance of something, perhaps 40 cm, usually for a typical size of evaporation chamber. So this H is roughly, well, 30-40 cm is probably quite a long distance. Maybe, yeah, I don't know, maybe 2 cm. So it depends on the chamber itself, the size of the chamber. It can be longer than that, it can be shorter than that. But more or less, it's somewhere there. Memberi panjang pendek sikit kot. So 30 cm less than 30 cm. So that's the distance that the precursor material has to travel before landing on the substrate. Right? You have T source, temperature of the source, you have T substrate. You can also have a system where you can control the substrate temperature in order to control the morphology or the crystallinity of the film deposited on the substrate. It can be done as well. So this evaporation flux is the material that you want to evaporate. And then if you notice in this particular process, so the line of deposition from the precursor material up to your sample is just a straight line. Dia tak akan pergi ke area like that. So it's just a straight line. So that's why we call it line of sight deposition. Apa yang dia akan, apa yang straight dia akan deposit. So kalau you ada precursor material kat bawah, but then your sample is way out of the diameter, jauh ke tepi, then you won't have anything deposited on your substrate. So you need to put it right on top of the precursor material, so at a straight line. So we call it line of sight deposition. So the evaporant here would be your aluminium, the material that you want to evaporate or you want to deposit. So it's a line of sight. And then mean free path here means for the material, for the precursor material to be deposited on the substrate, so it has to encounter minimal resistance along the way. Ini kita lihat, kita boleh bagi dia punya perjalanan tu terlalu resistive in the sense that you have too many particles in between. So in order to have less particles in between, you have to evacuate the chamber low enough pressure. At a low enough pressure, then only less particles can be found in between, right? So mean free path. So kalau ada too many particles ataupun chamber vacuum level is not low enough, so that means you have quite a number of particles available in the chamber. So these particles are going to affect the journey of your precursor material to the substrate. So they can experience some collision, and that will actually kill your material faster than dia tak akan sampai kepada substrate, because it has to encounter so many resistance by existing particles along the way. So that's called mean free path. So the longer it can travel at a particular vacuum level is better for a deposition process. Okay. Then eventually it's going to be deposited on your substrate, right? Deposited flux is basically your material, aluminium in this case. It's going to be deposited on the substrate, and then you have, after the process, you're going to have your film deposited on your substrate, glass, wafer, whatever lah. So these are among the parameters that you have to know during a typical evaporation process. Okay. Hearth design, so H, and then process parameters like temperature, and all other parameters. You want to control a few parameters such as film thickness, impurity concentration, defect density, and if you have deposited a dope material, for example, katalah you ada P silicon, well, that can be done as well, but then it will not be so accurate because there's going to be some melting involved in the process, so you may not have the right stoichiometry of the material on the substrate. Okay, usually if you want to do this deposition, it can be done on elementary material like aluminium or silicon. What if, my question to you, what if you want to deposit two material? Kalau you nak deposit cadmium, a compound, binary, cadmium telluride. You have cadmium and tellurium, but together they are cadmium telluride. Can you do a deposition by evaporation? What do you think? Boleh tak kita buat deposition by evaporation? Any guess? Can or not? What do you think? Anyone says yes? Anyone says no? No one says anything?
Doctor?
Yep.
As in element or compound?
Okay. Your precursor material is a compound, cadmium telluride powder, for example, and you want to have the exact compound on the substrate. Can you do that by this system? Rasa-rasa lah, logik boleh ke?
Yes, I guess.
Really? Will it be exactly the same as what you use for the evaporation? It may be yes, but most of the time, katalah you nak evaporate, for example, if you talk about solar, ada teknologi yang kita panggil CZTS. CZTS. Copper, zinc, tin, sulfide. CZTS, 4 elemen dalam compound tu. But eventually you want to have CZTS at the very end, at the other end. So you want to have exactly CZTS on your substrate, glass, wafer, whatever. But there may be a risk, or typically high risk, of you not getting the exact compound on the substrate as the original CZTS. So this is called stoichiometry issue, stoichiometry. So you want to have exactly as the precursor material, but you don't end up exactly as the precursor material, because when you do the melting process, so some bonds are broken, then it could be traveling at different pace with different speed, and they have different collision rate, something like that maybe. Then they end up as slightly different compound on the substrate. So this is called stoichiometry problem. So on the other hand, if you want to have a stoichiometric deposition, maksudnya you nak dapat exactly the same thing, typically if you want to do by evaporation process for this particular material, CZTS, you need to use 4 different sources. C satu source, maksudnya akan ada C satu source, X satu source, T satu source, and maybe another one satu source. So you need to have like 4 sources controlled by 4 different levels of current in order to evaporate them together and end up as a stoichiometric layer on the substrate. Kalau nak buat satu elemennya straightforward silver ke, aluminium ke, I know some other metals ke, ataupun perhaps silicon or some other material zinc ke, then it's going to be a lot straightforward. But if you talk about binary ataupun more than that, then you want to end up with stoichiometric deposition, stoichiometric layer on the substrate. Then if you want to do by evaporation, then you have to use multiple sources in your system, right? So if you talk about C, Z, T, S, then it's going to be like C for Z, for T, for S. Then only you're going to end up with the stoichiometric material on the layer, on the substrate, sorry. Okay. So I think I'm just gonna stop here. It's 12:57. Nanti kita akan continue tomorrow, right? So tomorrow we're gonna move on to the next part. We're gonna continue with evaporation, and then we're gonna move to other stuff related to PVD, and then on the sputtering itself. Okay, any questions so far? Okay, tak ada apa? All good, right? If no questions, then I'll see you tomorrow, inshallah. Bye-bye. Thank you. Assalamualaikum.